This physics lab will deal with the oscillation of a spring mass system. The goal of this lab is to observe oscillating motion of a spring mass system that moves in the x and y direction. We know the mass of this to be 0.402 kilograms, and we're going to model the motion of the system in Python. Our first step is to determine the system, and I chose my system to be the mass, the spring, and the earth all together. This is important for the energy principle, and we'll discuss this later. The first thing we need to do is find the spring constant K. It was determined to be 6.83 newtons per meter from the lecture videos using this formula, where T is the period of oscillation, and we can rearrange this formula where K is equal to 4 pi squared mass over the period. We also need to find the relaxed length of the spring. We know the mass is initially at rest when the spring is 0.7 meters long, and that is our L in this case. And when the spring is at rest, the force of the spring must equal the gravitational force, so mg must equal K times S. We can replace S with L minus L naught and rearrange this equation to find L naught to be 0.123 meters. This is the code that we use to initialize our model, where gravity is 9.8, our spring constant 6.83, our L naught's 0.123, and we also have L, which is the length of the spring, where we took the ball position minus the spring position. L hat is L over the magnitude of L, and S is the stretch of the spring, which is the magnitude of L minus the relaxed length of the spring. Now, this motion seems very complicated, however we can use Newton's second law to predict it. Newton's second law is shown here, where velocity final is velocity initial plus the net force of our mass times delta t. We know in this case only the force of gravity and the force of the spring are acting on this object. So we set these up appropriately, where the force of gravity is mass times gravity in the negative y direction, and the force of the spring is negative k times s times L hat, and F net is adding these two things together. We update the ball's velocity and position accordingly, like we have in previous labs, where the velocity is the old velocity plus the net force over mass times delta t, and the new position is the old position plus our velocity times delta t. So the next thing we need to do is talk about the energy principle. The energy principle is saying that the change in the total system energy must be equal to all the energy transfers with the surroundings. Because I chose the system to include the Earth, in our system there are not any interactions that transfer energy to and from the surroundings. We are assuming a neglection of air resistance and the mass of the spring. So the total change in energy is going to be the change in kinetic energy plus the change in potential gravitational energy plus the change in potential spring energy, and this will all be equal to 0. To find the kinetic energy, we simply take the kinetic final minus kinetic initial at each time step. To calculate the kinetic energy, we do 1/2 mass times velocity squared at any given point. Finding the gravitational potential energy is of a similar algorithm. We take the gravitational potential final minus gravitational potential initial, and we use this formula, mass times gravity times the y position, to calculate this. We also need to find the spring potential energy. This is similar, where we have the spring potential final minus spring potential initial, and to get the spring potential energy we have 1/2 k times s squared, which was a formula given to us, where s is the stretch of the spring, which is L minus L naught. And we also wanted to model the observed motion, so I read in a CSV file with the observed positions that were obtained from tracker and used this code to model the observed motion as a red ball, where we have ball2 position is reading in the x and y coordinates from the tracker file. Here's a video of my model in action, where you can see the blue is the model ball and the red is the observed ball from tracker, and we have our energy graph here, which I will discuss in a moment. So here's our energy model, where the total change in energy is the yellow line, which is equal to 0 all the way across, which is what we expected. That means the energy principle is satisfied because there should be no total change in energy. We also have the blue as our change in kinetic energy, the green is our change in potential gravitational, and the red is the change in spring potential. And all of these, the kinetic, potential gravitational, potential spring, cancel out to be 0 for our total energy. Here the x and y position versus time comparisons, where our model is in blue and our observed motion from the CSV file is in red. They match up quite closely, but differences may be caused by the motion in the z-plane, or air resistance, or the fact that we did not account for the spring having mass in our model. And also, is it possible to get two separate oscillation periods? Yes, you can get two separate oscillation periods for the x and the y. I have my y oscillation to be 1.524 and my x to be 1.646. The difference is small, but this means that the x oscillation will take a little bit longer to complete.